Alright guys, I am back finally. Sorry for the long delay in videos. I've been very busy with life. So we're going to do problem 1.20, finish out this chapter, and then we're going to try to finish the rest of these questions, and then move on to chapter 2, the rest of the chapter 2 questions, and then keep continuing this. I'm still serious. It's going to take me a long time, maybe a year or two, so hopefully by the end I'll finish this whole book, and then, at that point, I don't know, maybe I have some level of coherency about this. Also, if you guys are interested in following Jesus, or you want to be a Christian, become a Christian, or give your life to Jesus, click some of the links. I'll leave some links down below. Just click some of those links and give it a shot if that's, something you've felt. Anyway, let's go to problem 1.20. So it says, given the spectrum gx of f, and g of x is a sinc function, find the value of the signal bandwidth using the following bandwidth definitions. Half power bandwidth, noise equivalent bandwidth, null-to-null bandwidth, 99% of power bandwidth, bandwidth beyond which attenuation is 35 dB, and absolute bandwidth. Alrighty, so we have a function. It's a sinc function, so we have a function. It's called g. So we're going to given. We have a function. It's gx of f, and it's equal to 10 to the minus 4 sine of, let's see here, pi. So pi times f minus 10 to the 6. Is that what it is? 10 to the 6. So it's shifted over right, 10 to the 6. So it's at basically a megahertz, I believe. And then 10 to the minus 4 times 10 to the minus 4. And then all of that. And then divided by the inside. So pi f 6 times 10 to the minus 4. And all that squared. And so what they want us to do is find half power, so half power bandwidth. Half power bandwidth is a 3 dB bandwidth, so 3 dB bandwidth. 3 dB is over half the power, right? Because 3 dB is about 1.999 in linear. 3 dB is logarithmic, so you get linear, it's about 1.99. Then they want us to find the noise equivalent bandwidth, which is, so I don't know what the symbol for noise equivalent is, but I think it's ENBW, something like that. Equivalent noise bandwidth. So they want us to find that. And they want us to find null-to-null, so I usually say N to N BW. These are just notations I use. I think this is a common notation, this is a common notation. This one I'm not sure what null-to-null is officially, but I always use N to N. They want us to find 99% power bandwidth. So this is some FCC stuff, so FCC, we'll put a smiley face. They're the reason we can put videos up on the internet and transmit and do things of that nature, so don't want to offend anybody. And E, they want us to find the power beyond which the attenuation is 35 dB. So 35 dB attenuation, which could be troublesome to find. And then F is the absolute bandwidth, which we know is going to be infinite because this is a time-limited signal, but we'll get to that. So let's start with the first one. So let's start with finding the half power 3 dB bandwidth. So what is the 3 dB bandwidth? That is the relevant question. And to get a sense of that, we first have to figure out what does our function even look like to find the 3 dB bandwidth. So our function is a sinc function. And a sinc is a sine x over x function. So a sinc function, if you ever see sinc of x, that means sine of x over x. Or sometimes we normalize it. It's pi x, so it'll be sinc. Sometimes sinc of x really will be sine of pi x over pi x. And this is sometimes used in signal processing people, and people that like to do math and stuff do this. But you can use either one. One's normalized, one's not, by pi. And so a sinc function looks like this, and you specifically when it's squared here, it's squared. So when it's squared, a regular sinc function rather. Let's just do a regular sinc function. is going to look like, it's going to have a amplitude, a max at x equals 0. Go down, and it's going to keep doing like that. Boop! It's like that, right? This is a sinc function here with it. It has a maximum at x equals 0. So this is the max at x equals 0. And it keeps oscillating infinitely, but each oscillation is getting smaller and smaller because this x term is growing as x goes that way, or frequency or time, whatever we're talking about. As this grows, this denominator gets bigger, and so this whole thing gets smaller because sine is bounded in between -1 and 1. So you keep having like -1 divided by 5, 1 divided by 7, 1 divided by 8 as x goes further on and further on in time. But here we have a sinc squared function, right? So sinc squared, I'm going to just draw it real quick, is the same thing, but all these negative lobes get flipped up here to the positive axis. So now you end up with something like that. And on this side, you end up with something like that. And you see all the negative lobes get flipped up because they're getting squares and multiplied by itself, so there are no negative components, they're just positive components. So you still have a max here at x equals 0. Now technically you'll notice that at here x equals 0, when you plug in 0 for x, you should get something divided by 0, which is going to be not computable. We talk about the limit of this x equals 0 is 1 essentially. And so we use that convention, but in a technicality, yes, when you plug x equals 0 here, you do get undefined. But here we talk about sinc, it's being defined at that point because we're talking about limits. So now that we've kind of discussed what this is, let's talk about a little bit about finding all these bandwidths. And this is going to be the real interesting part of this video. Let me just get a paper towel to clear this off, and then we'll get into that. Alright, so I just got a paper towel. So let's go ahead and talk about this 3 dB. So 3 dB means when half of the power, when this function has reached half of the power of its maximum power. Well, we know what the sinc function is. It's 1, right? The max is always at x equals 0, which is the center frequency of the sine, right? We talk about center frequency, we're talking about a signal now. When you sinc, right? When it's at its center frequency, so let's say it's a baseband, non-modulated, it's at center at x equals 0, and it's going to be 1. Well, here we have a multiplier. So the multiplier is going to make the maximum value whatever the multiplier is, because this inside part, when squared, is going to compute to 1, and then you multiply it by 10 to the minus 4. So the max of our function, so the max of gx of f at, here it's actually at f, it's actually shifted at 10 to the 6, so the max at g of x is at 10 to the 6, f is equal to 10 to the 6, so it's shifted, the center frequency usually is at 0, but now it's shifted over to 10 to the 6, right, which is a megahertz, or 1 meg, and this is going to actually now be equal to 10 to the minus 4. Because we have this multiplier here out front that gets multiplied by this part, which traditionally would evaluate to 1, but now we multiply by 10 to the minus 4. So this is our maximum value. Now we want to find when sinc is equal to half of this. Well, okay, well half of that is just 10 to the minus 4 divided by 2. So we say 10 to the minus 4 divided by 2 is equal to, and we want to find at what frequency value this is the case. Because if we find out what frequency this is the case, then we'll know on one side it'll be equal to that, and the other side will be equal to that, and then we find the distance between the two, and that will give us our 3 dB bandwidth. So basically what I'm saying here is we have the main lobe, right? And let's say at this point right here is 3 dB, right? Well, we find this F, right? And we find this F, and we find this distance between them, that equals our 3 dB bandwidth. Because that's the distance in between where half of the power, from this distance is where half of the power, greater than half the power is centered at. After that, half the power falls off. And so here what we want to do is set our function equals to this value. So we do sine of pi of f minus 10 to the 6 times 10 to the minus 4 over pi f minus 10 to the 6, 10 to the minus 4. This is squared, by the way. Squared. I'm going to do a change of variables here. It just makes it a lot easier. It just makes it a lot less of a hassle, honestly. So when we do change the variables, basically say, okay, so I'm going to set x equal to the inside part here. So now when I solve for x, I'll substitute this back in and compute what f was. So now, substituting in this end, you'll see it makes it a lot simpler, right? So here you're going to get sine of x, right? This inside part is x, and then you have x on the bottom because this is x here, and then you have all this squared. So what you end up with is sine squared of x over x squared is equal to 10 to the minus 4 divided by 2. So what you do is, okay, you divide this. This is going to be 1/2. So this is going to end up being 1/2 is equal to. Whoops, I'm sorry. 1/2 times 10 to the minus 4 is equal to sine squared of x over x squared. Now, to compute this, you're not going to be able to do this with just algebraic techniques. You're going to have to do this numerically. That's trying different values. I used a calculator online, and I got that x. So you also can use a graphical method. You can use a graph to find this. I use a calculator because anytime you're computing sync, you're going to want to use numerical methods. So x is approximately equal to 1.4 here. And so that's x, right? But x is a change of variables that we did. So we need to substitute this back in here for x. So what we say is, okay, so pi of f, because remember x is this. X is pi of f minus 10 to the 6 times 10 to the minus 4. So f, that's 10 to the 6, 10 to the minus 4, is approximately equal. And we'll drop the approximation. We'll just say it's equal to 1.4 because it's relative. It's equal to this. So then what you end up with is f is equal to 1.4. I'm going to divide by 10 pi, divide by 10 to the minus 4, and then I'm going to add 10 to the. I'm going to add 10 to the 6 here, but it's not going to make that much of a difference. Oh shoot! Hold on, wait a minute. I put 10 to the 6. Let's see here. Is that 10 to the 6? 10 to the minus 6. Yeah, it's 10 to the 6. Okay. So it's going to be 1.4 divided by pi times 10 to the minus 4 plus 10 to the 6, which approximately is about, you end up with, what is it, 4.46 kilohertz. And then that's this frequency when it's less than that. So you multiply it by 2, right? Because this is the bandwidth is going to be twice. You have one f on one side, f on the other side. So 4.46 kilohertz is that value, and then again at twice that amount, it's this value. So it's going to be equal to 8.9127 kilohertz. And that'll be our 3 dB bandwidth. So this is our computation for our 3 dB bandwidth. So we found that it's when we have a signal, a sync function that's like this, and our max value is 10 to the minus 4, where half of this 10 to the minus 4 falls off, is going to be in between this 8.917 kilohertz center at 10 to the 6 hertz. That's at 1 megahertz. You get about 10 kilohertz of bandwidth, which is not that much, but it's something, right? So we solved that half power 3 dB bandwidth. Now let's solve the ENBW, right? So the ENBW is the equivalent noise power rectangular bandwidth. Essentially, what that is you have a function. I mean, you have a filter. Like I say, filter. Here's a function, or here's an actual, let's say a filter that, or it's a time signal. I don't know what it is, right? We can only represent it as a function. It doesn't matter. We have a function, right? It has some area underneath it with some area underneath it. It has all these lobes, and inside these lobes is where the function oscillates at, and it has a voltage, and it has power at those values, at those frequencies. So you find the power, right? First you find the max power. Max power and then you find the total power. And what you do is say, okay, well, I can make a window filter. So a window filter, it's kind of like one of these. It looks like a rect. It's basically a rectangle. And that rectangle has the max power, the same max power as your filter power, and it has the total power of the total power as its area. So the total power underneath this filter is also is enclosed in this. So this area here, this area is equal to the total power of your filter. And so this is kind of a technique to get a sense of, you know, what filter would I need that would replicate, you know, the noise or power of my initial design filter or my initial signal. And so it finds its uses in various places. And here the author wants us to just see how that's calculated and get an initial feel for it. So my initial feel for it is, how do I calculate it? So to calculate the E and BW, so calculate that, you need to find the total power of the signal divided by its maximum value. And so the total power of our signal is the computation so px is going to be equal to the integral from -infinity to infinity, because this signal goes from -infinity to infinity. It's not band limited, it's band infinite. Of our function, which is going to be sinc divided by wn here. It's going to be sinc. So I'm gonna do a change of variables again. I'm going to do a change of variables again. Squared over x squared. Dx here. And then divided by wn. Wn is the maximum value. So this is the max value of our function. Well, the max value, you already calculated that in the previous half power 3 dB. It's 10 to the minus 4. 10 to the minus 4 is the max power. It's the max value. It's always at the main lobe, at the maximum of the main lobe. Our main lobe it's centered at 10 to the 6, so 1 megahertz. So let's talk about this change of variables here before we compute. Let's talk about something else before we even talk about change. Let's talk about something here. So how do you go about computing this? Well, you don't. There's already people that did that much smarter than you and I. Maybe not. Maybe you're smarter than I know I'm not. But basically, what the computation comes out to is using very tricky math, but computation from -infinity to infinity of a non-normalized sinc function, so that would just be a regular sine of x over x, dx is equal to pi. The integral from -infinity to infinity of sine squared of x, guess what that is? Well, it's also pi. Why that is the case, I don't know. I don't have the answer. But I know that these two are both equal to pi. And so we can use this we can basically use this tool to our advantage. We have this easy value, we know it's pi, and so it makes it easy when we do the computation. Another interesting fact we're going to need is the fact that the antiderivative of sine x over x dx, or sine squared of x squared, is going to be equal to what's called the sine integral plus c plus this constant. And this is a tabular form of this antiderivative here, and so you can look this function up and find a table for it, and then you find what x values you need. And someone went about computing this antiderivative and did math methods to figure this out. So we leverage these three ideas here to compute our E and BW, because it involves us integrating a sine function. It doesn't always involve integrating a sine function. It just happens to be that our function for our power is a sinc function, and so we need to be able to integrate the sinc function. So let's talk about let's erase this and talk a little bit about how we're going to do this change of variables. The change of variables is going to be here. we're going to obviously do how we did before. So pi of f, this time it's going to be different though, just a little bit. So pi f minus 10 to the 6 times 10 to the minus 4 is going to be equal to x, right? Okay, but here's inside an integral, and we're integrating with respect to f, so we need to, when we do a change variable, we need to integrate with respect to x now. So before we integrate with respect to f, now we're integrating with respect to x. So now what we do is we say, okay, well, we differentiate this, right? When we differentiate this, what we're going to get is we're going to get pi 10 to the minus 4, because 10 to the minus 4 pi f, when you take, so what I'm saying is we take the derivative, right, with respect to f over here. When I'm doing a basic change of variables here. And then on this side, we're going to get dx. And this side, we're going to get df, so we're going to take the derivative. So the derivative of this side is going to give me pi times f times 10 to the minus 4. So we take in respect to f is going to be pi 10 to the minus 4. So you get df pi 10 to the minus 4. And on this side, you just get dx. Okay, so we have to replace this with our function. So we know in the original function, we do have a 10 to the minus 4, which is found here. But we don't have a pi, so we have to divide this pi on both sides. And so what we end up with is a df 10 to the minus 4 is equal to pi dx, which is cool. So we just have to, it's actually divided by pi rather. So 1 over pi. So 1 over pi dx. And when we go up here, we have to actually substitute in times 1 over pi. So times 1 over pi dx. And we need to take this 1 over pi outside because it's not dependent on x. And so what we end up with is 1 over pi minus infinity to infinity of sine squared of x over x squared dx divided by 10 to the minus 4. Okay, well we know that from earlier we know that this equates to pi. So what we get is 1 over pi times pi divided by 10 to the minus 4. Well, we have pi times 1 over pi, so those cancel. And then we end up with 1 over 10 to the minus 4. Well, that is 10 to the minus 4. So this is the same thing as saying 10 to the minus 4, which is 10 to the 4. And that 10 to the 4th is 10, 100, 1,000, 10,000. So that's going to be 10 kilohertz. So 10 kilohertz. And so we end up with the ENBW of 10 kilohertz. And this would be the bandwidth of that filter I was talking about earlier. That has the same amplitude and the same area power underneath. So the filter bandwidth, and I'll do it right here. Just erase that for a minute. Right, the filter bandwidth is going to be 10 kilohertz. Right. So that's not too bad. That question was pretty straightforward, pretty simple. So it just took a little bit of computation, and then we had to get it all right. Once we got it right, it made sense. So that's a filter that would end up having the exact same power, peak squared power, as well as having the same total area underneath it. We were to create a filter that emulated the behavior of our power function. So I feel we did the first three. Let's go ahead and do one more, and then we'll pause it, and then the next video, we'll solve the last three. Let's do the null-to-null. This one is really, really easy because we have such a well-defined signal. When you have a well-defined signal like a sync, it has zeros, which are called nulls, and that's where no power, at that frequency, there's no power. And that happens naturally because, sine has zeros, right? So the sine function, so let's say sine x, right, has zeros at, what is it, pi, pi, okay, well, let's see, at 0, pi, 2 pi, 3 pi, 4 pi, so on and so on. So sine has zeros, and at those values, this function this part will evaluate to 0. And so when it evaluates to 0, you have no power at that frequency. And so what it wants us to do is find the nulls of the first bandwidth, the first lobe, right? The main lobe, actually. And so the nulls can be found. when you have a function that's very well defined, like what we have here, which is not always realistic, but you know, sometimes it is, sometimes it's not. But here it's well defined. So at this lobe here, right? Let's just say this is 10 to the 6. Let's say this f equals 10 to the 6. Right? This is going to be our first lobe. So this is going to be FC. Because this is, FC stands for center frequency. So this is our center frequency. This is going to be FC minus 1 over T, I believe. And this is going to be FC plus 1 over T. So what is 1 over T? Well, 1 over T is the period, which is equal to the frequency of our function. So every period, every sample period, every interval sample period, this function right here, power equates to 0 for the sinc function, for the way the sinc function is defined. And so what that means is we have to find what this is. Well, actually it's given to us, but it's just kind of hidden. So in the way our function is defined, our t, our interval, that is actually going to be this value right here. 10 to the minus 4 is equal to our t. And why that is the case? Well, that's the way they define the sinc function for this problem. Specifically for this problem. That's not always the case. Sometimes you're going to have to compute what this 1 over t is. But here they gave us that t is equal to 10 over minus 4. So all we need to do is plug in. All we need to do is find this distance, right? So this distance between the nulls would give us the bandwidth, the null-to-null of the first lobe. And the reason that's important is there are regulations and standards talking about how much your lobe, you know, your main lobe has to be down to not interfere with other signals that are sharing frequency. People talk a lot about lobes, but sometimes, you know, more about 3 dB and 35 dB because, you know, FCC. Anyway, try to follow the FCC. So whatever rules and regulations they have, that's important. People also care a lot about the first lobe, or the main lobe where the frequency is centered at. So to find this distance here, we're going to take FC. So we know FC is 10 to the 6. Right? We're at 1 meg, and our frequency, our sampling is 1 over 10 to the minus 4. Right? And we're going to subtract, So what we do is, whenever you want to find distance between two points, right? It's the same principle here. I try to remind myself of this so I don't go crazy. I want to find the distance between B and A. I take the furthest point, B, and I subtract it from A. And that gives me the distance. Or you take A, subtract it from B, and take the absolute value, I think. Not sure. You know, y'all have to fact check that. But anyway. So here on the left-hand side, on the right-hand side, we have 10 to the 6 plus 1 over 10 to the minus 4. On the left-hand side, we have 10 to the 6 minus 1 over 10 to the minus 4. Well, okay, let's do some subtracting. 10 to the 6 minus 10 to the 6 is 0. That goes away. But here we have 1 minus 1 to 10. So this is going to be 1 over 10 to the minus 4, the same denominator. 1 plus 1 over 10 to the minus 4. That's 2 over 10 to the minus 4, which if I did my math correctly, that is 2 times 10 to the 4th. That's going to be 20 kilohertz. 20 kilohertz, I think so. 20 kilohertz. Let's just fact check that real quick. Yep, 20 kilohertz. So this is going to be our null-to-null bandwidth. So we just completed our null bandwidth. And so that means, you know, 20 from 10 to the 6, go 20 kilohertz to the left, no power. 20 kilohertz to the right, no power. And then the lobe repeats again, but it's a side lobe and the power is lower. You don't get that 10 to the minus 4 because the denominator starts to increase and decrease the power. But you'll find so 10 to the 6 minus 20 kilohertz gives you, so 1 meg is 1,000 kilohertz, or I guess, yeah, 1,000 kilohertz, 1 meg, I believe. So 20 kilohertz minus 1,000, so this end up being 980 kilohertz. So at 980 kilohertz, the power, so the gx of f equal to 0. And then 20 above that, so then you get 1020 kilohertz. The power again is 0. It's just the nature of the function. So this is going to be the first 3. We're going to cover the next 3 tomorrow. Get that video out so you guys can understand that. And hopefully this was helpful. If you guys liked it, just leave a comment if you didn't understand. Also leave a comment. I'm out.